Okay, good morning, Math Studies. All right, today we're going to take a look at more about instantaneous rates of change using something called the derivative. Now, in the last section, we talked about finding the instantaneous rate of change by drawing a tangent line at the point that we were interested in finding the slope of the curve at, and then counting the slope of that line. Now, the problem is, when we drew that line in, some of us might have drawn a line in like that, whereas some of us might have drawn the line like that, simply because, well, we're just using our eyes to find that tangent line. And so our accuracy of drawing that tangent line, well, it's different for each person, correct? So even though that's the main idea of this, we want to have a more formulaic way of doing this, a more algebraic way of doing this. And that's what we're going to talk about today. We're going to talk about finding the instantaneous rate of change, or the slope of a function at a given point, using something called the derivative. Now, the derivative is going to be an equation that finds the instantaneous rate of change or the slope of a graph at any point on the graph. The notation that we're going to use for the derivative is f apostrophe x, we call that f prime of x, y prime, or we'll also call it dy over dx. Now, why is it called dy over dx? Well, the dy basically stands for the difference or the change in my y values, and the dx stands for the change in my x values. Okay? Which is really what the slope formula is. It's change in y over change in x. But we'll be finding this, obviously, instead of using 2 points, we're going to be using only 1 point. Now, this formula comes from some calculus ideas, something more specifically called the limit process of the slope, which we don't need to know in IB, but this formula will be used to find the derivative of a function. Okay, here are the steps you're going to have to do. To find the derivative, we're going to take a function like f of x equals a times x to the n. Now, this a is my coefficient, remember, from algebra, and this n is my exponent. Well, to find the derivative, all you simply are going to do is you're going to take this exponent and you're going to multiply him by whatever the coefficient in front of x is. All right, so you're going to multiply the old exponent, n, by a, and then to create the new exponent of x, you're going to subtract 1 from the old exponent. Okay, and that's it. So let's take a look at some examples here. It says find the derivative f prime of x given this function f of x equals 5x cubed. Well, to find the derivative, all I'm simply going to do is say the derivative equals, the 3 is going to come down to the front and multiply by the 5 times x, and then you're going to subtract 1 from 3. Oops. You're going to subtract 1 from 3. So the derivative of this guy will simply be 15x squared. And that's the derivative. Now again, his purpose, this is going to be the equation that finds the slope. So realistically, if you wanted to think about this derivative, this is the same thing as what we used to call m back in algebra, right? Alright, so ultimately, this graph of 5x cubed, if I wanted to say find the slope of this graph at a single value, say when x equals 1, I would just plug a 1 in here, and that would tell me the slope of that graph. Okay, let's take a look at another example. If I've got f of x equals 3 over x to the 4th, here's where I've got an issue. My issue with this is this variable is in the denominator, right? For you to take the derivative, x can't be in the denominator. So what we have to do is we have to rewrite this equation in what I call derivative-friendly form before we can actually take the derivative. So to do that, I'm going to say f of x equals, notice I haven't taken the derivative yet. You learned back in algebra negative exponents, and this is one of the big reasons why negative exponents were taught to us in algebra, is so that we can take the derivative of functions like this, 3 divided by x to the fourth. Well, I can rewrite this as 3 times x to the negative 4 power. Remember that we can move bases and their exponents from top to bottom and bottom to top, either by giving negative exponents or taking away negative exponents. Again, I hope we remember that from algebra. So now my new function can be written as 3x to the negative 4. Now this is derivative friendly, and I'm ready to take the derivative. So now the derivative would be, well, let's see, this old exponent comes to the front, so it'll be negative 4 times 3x to the, and again I've got to subtract 1. So negative 4 minus 1 become to the negative 5th power. Now that I've taken the derivative, I'm just going to simplify this and say that would equal negative 12, because negative 4 times 3 is negative 12, over, now this x to the negative 5th. Now that he's served his purpose of taking the derivative, I'm going to move him back to the bottom and call this negative 12 over x to the 5th. And so that's the derivative of this function. And again, I remind you, the whole purpose of this is this equation can now find the slope of this function at any x value. Now, my question to you is, in this problem, what is the only x value where the derivative won't exist? That's right. It's going to be at x can't be 0. Because if you think back to the original function, if you let x equal 0 here, this becomes an undefined fraction, so the graph doesn't even exist at x equals 0. Okay, the next problem. The next idea is just following along with what we've been doing, but now we're actually going to find some slopes. This says find the gradient, which again is the IB way of saying slope. In other words, dy dx. Then find the gradient at the given value of x. So in this first example, I've got f of x equals negative 4x squared, where x is equal to 3. So what I want to do is I'm going to hold off on this guy right here. I'm going to hold off on him for now. I'm just going to find the derivative. So the derivative of this guy, using the power rule, says bring the 2 to the front, so 2 times negative 4x, and then you have to subtract 1 from 2, so the 2 minus 1 is 1. So my derivative is going to be negative 8x. Well, again, to find the gradient or the slope of this original function at x equals 3, I'm just going to simply plug in a 3 for x. So the slope of negative 4x squared at x equals 3 would equal negative 24, which tells me that this guy will be, the graph will be going down at this point. It will be downward, and it's going to be a pretty steep slope. So something really downward like that. Okay? And then on this last example, if I've got f of x equals 2 over x cubed, I'm actually going to find the slope of this guy at this point on the graph. And again, if you do the math, if you plug a 3 in for x, wouldn't you get 2 over 27 for the y value? Okay, to find the derivative then, again, I'm not ready to take the derivative. I first have to write this in derivative-friendly form, which would be 2x to the negative 3. Now I can take the derivative, which would be negative 6x to the negative 4. Does everyone hopefully understand well how I got that? And now, out of this point, all I care about, this has to find the gradient or the derivative at a given x value. I need an x number. So out of these two values up here, which value am I going to use? I'm only going to use the 3. I don't care about the y because there is no y in this equation. So if I find f prime at 3 again, I would get negative 6 times 3 to the negative 4 power. which is the same thing as saying f prime at 3 equals negative 6 over 3 to the 4th. I moved the 3 back down, and that would become negative 6 over, well, 3 to the 4th is 81, and I think that both of these top and bottom can be divided by 3, so I get negative 2 over 27. So in this case, this graph, it would be going downward because it has a negative slope at that point, but the slope is only 2 over 27, so the rise would only be 2 and the run would be 27, so it's not a very steep slope at that point. And that's it for section C. Talk to you later.